So we reviewed acids and bases and how there are three different definitions, the Arrhenius, Lewis, and Bronsted-Lowry definitions of acid and bases. But what we've learned up to this point is that all acids and bases ionize. Okay, they ionize. And what does that word ionize mean? It means the compound forms ions. Basically, it dissociates. It goes from a compound to the two ions that make it up. And so when we're talking about acids and bases, and when we're talking about the strength of acids and bases, essentially what we're talking about is how much those molecules are dissociating. So let's talk about the most basic example we can think of, water. Okay? Water, H2O liquid, can be expressed as an equilibrium with hydroxide ion and hydrogen ion, H+. Okay? This exists in an equilibrium, okay, favoring one side or the other, and if it exists in an equilibrium, we can write an equilibrium expression for it. So K would be equal to the concentration of OH minus times the concentration of H plus, divided by nothing because H2O is expressed as a liquid, so it's not included. Now we know for water, the concentrations of OH minus and H plus are constant for pure water. So instead of writing this as just K, we actually can express this as KW, equilibrium constant for pure water. And for pure water, the concentration of each one of these values is 1.0 times 10 to the negative 7. So if we wanted to know what the equilibrium constant K is for these concentrations of pure water, we would just plug those values in. So this would be 1.0 times 10 to the negative 7th times 1.0 times 10 to the negative 7th, which would essentially give us 1.0 times 10 to the negative 14. Now, this is an important value to know. It will help us a lot when we start dealing with buffers and equilibrium of acids and bases and trying to calculate specific concentrations. And this is referred to as, like I said, KW. This is also given on your AP equation sheet, so there's no need to necessarily memorize it, but it's something that you use frequently enough that you do want to have it memorized. We can use the same concept of the equilibrium constant for any acid and base to determine the strength of that acid and base. Okay, so we reviewed today Bronsted-Lowry acids and bases and their conjugate acids and bases. And we've learned that if you increase the strength of an acid, what that does is it represents a decrease in strength of the conjugate base. Okay? So for example, HCl is a strong acid. Its conjugate base would be, after this dissociates, its conjugate base would be Cl minus. Cl minus is actually a very weak base because HCl is a very strong acid. Now those are just relative conceptual explanations, but what we need to be able to do is to quantify them. We need to be able to quantify and measure exactly the difference in strength between acids and bases. The way we do this is we use something called the acid dissociation constant, which will be expressed K sub A. And again, this is an equilibrium constant, that's why we use the value of K. But let's talk about an example, a generic example of any acid and how we would write the Ka value. So let's pretend we just have acid HA, where A could represent any anion, and it's in a solution. We mix it with water, H2O liquid. Okay, and we know it's going to be in equilibrium, forming H3O plus, which is called a hydronium ion. You need to know exactly what this term is. I don't think we used it in CP chemistry. Hydronium ion, which is basically the same thing as H plus. Solution of that plus A minus. A quick little review for you to do would be to identify the acid, base, conjugate acid, and conjugate base in this example. So give yourself a shot at doing that right now. This would be the acid, because it's donating a hydrogen, so therefore this would be the conjugate base. Water would be the base, because it's accepting a hydrogen, making H3O plus the conjugate acid. But now if we wanted to quantify the strength of this acid, HA, we want to know how strong is HA. The way we would do that is we would write the acid dissociation constant, which is called Ka. The acid dissociation constant would be written just like any other equilibrium, so it would be the concentration of H3O plus times the concentration of A minus, all divided by the concentration of HA. So this is an equilibrium representation of the acid dissociation constant. And conceptually what this means, as Ka increases in value, as it becomes a larger number, what that's representing is the value in the numerator here is getting greater, or the value in the denominator is getting smaller. That means we're forming more product, and one of our products is H3O plus. So the more H3O plus we form, we know that since pH is equal to negative log of H plus, H3O plus, same thing, we know that as Ka increases, we're forming more H plus, so pH is dropping, and essentially this means you have a stronger acid. So what you need to be able to do is compare compounds given their Ka values to compare the strengths of these. Now, one thing to note, this is only for weak acids. And the reason is because strong acids, we say, completely dissociate. So there is no leftover HA. All of HA dissociates into H3O plus and A minus. Ka values are only used for weak acids. The same thing can be done for weak bases. So for example, if we had the reaction with ammonia and water, ammonia is a weak base, so it would be in equilibrium with the ammonium ion, NH4 plus, and OH minus. So since this is forming a hydroxide ion, we know that this is a base, but now how do we quantify it? Well, we could write the equilibrium expression, K. We know this would be equal to the concentration of NH4 plus times the concentration of OH minus, all divided by the concentration of NH3. Since this is a unique example where we're talking about a base, this acid dissociation constant would be listed as Kb, and this would be called the base dissociation constant, because we use this for bases. But again, the same idea. It's writing an equilibrium expression, which we did over and over and over again last unit. And we just have to be able to solve quantitative problems using this. Same idea. As Kb gets larger, that means you're forming more OH minus, which means you have a stronger base.